Hey, everybody, welcome to another episode of Behind the Cape, and we're ready for part two. We've got, once again, fellow data superhero Ian Whitestone. Welcome, Ian. Happy to have you again.
Thank you. Glad to be here.
So before we get going, we really got into Snowflake observability. I can't even talk today. And maybe give a little recap of what we did the last episode and kind of what you're going to get into in today.
Yeah. So I think we had very grand ambitions for all the things we were going to cover in our last episode, and ended up maybe covering a 10th. So this is part two in an N series where N is TBD. Hopefully N is a large number because there's so much fun stuff to talk about on this subject. But yeah, I think, gosh, it's been a while, but if I remember correctly, we kind of talked a bit about the philosophy of optimization and kind of how to approach it from starting with understanding how does Snowflake actually build. So I think we got into the billing model. We talked about some of the different, I think we touched a bit on like the native cost optimization and monitoring features that right. Snowflake provides. I remember talking about query timeouts at one point and going on a bit of a ramble about like, don't necessarily set everything to an hour because an extra small an hour costs you like $2. It's not worth canceling someone's query for that. But anyways, yeah, I think we covered a bit about the high-level billing model, a bit on some of the native features, although I think we should definitely do a full episode on like going through what are all the features Snowflake offers for this, because there are a lot for another episode. And I think where we wanted to take things today is like taking that understanding of, okay, I'm trying to optimize my usage or ensure effective use of my credits. How does Snowflake bill? We talked about compute being oftentimes the largest driver of Snowflake credits. So when it comes to optimizing compute, you need to be optimizing the actual queries that are running in those warehouses and driving compute. So today we thought we'd focus a bit on helping Snowflake practitioners understand how they should go about the kind of vast topic of query optimization. So figured that would be a good place to take things today. What do you think?
Sure, sounds good. So you mean we don't just crank up the virtual warehouse sizes and just get more compute that solves the performance?
That can be a great way to make things run faster, but maybe not always the best way.
Absolutely. So yeah, let's get into it. What do you want me? Want to share your screen?
Cool. Yeah, I had some slides that I thought would be helpful just to kind of stare at instead of you looking at my face as we talk through some of this stuff. So these are kind of for actually context. I didn't even introduce myself. I'm the co-founder of a company called Select. We help Snowflake customers monitor, optimize, understand their Snowflake usage. As part of that, we try and write a bunch of helpful educational content so customers can understand what's going on under the hood and how to use things. So a lot of what I'm showing here is from either blog posts that we've written in the past or presentations we've done. So if you've followed some of what I've done in the past, I apologize. I may repeat myself a bit here. But that's where this is coming from. And we'll kind of link out to the relevant posts if people are interested in learning more. Where I wanted to dive in to start with is like a very quick recap of Snowflake's architecture itself. And that's an important bit to understand when you go about optimizing a query is you need to understand like how does data actually flow in the system and what are all the different steps in the process. So as a quick recap, for those who aren't familiar, Snowflake has these three different layers that are kind of independently scalable. And this is part of what makes Snowflake so great. Keith, I can't remember your background, but I'm sure you've worked, I imagine you've worked with like the Teradatas of the world.
Yes.
Where everything was fixed and you could only scale, like you kind of had to scale everything up at the same time. As people hopefully know now, like this is part of what makes Snowflake so magic. I'll end my fanboying there, but yeah, these three different layers. Each of them scale independently. You have the cloud services layer where a bunch of different things happen, which we'll get into. The compute layer, which is where like the meat of the query execution happens. And then a storage layer, which is separate from the compute. Snowflake runs on different cloud providers. This storage layer will be whatever the underlying cloud provider uses for storage. So if you're on Amazon, it would be S3. If you're on Azure, it would be Blob Storage. If you're on Google Cloud, I think they just call it cloud storage. So those are the different three layers. And I think what's most helpful to understand is like how these fit together is when you look at the life cycle of a query. So at the top left here, we have a analyst who is excited to go to work and run some queries in Snowflake. So you can see at the top left, they submit a query. So the first thing that happens when you submit a query to Snowflake is it goes into what's called a cloud services layer. There's a bunch of really important things that happen in here that are vital to like a query being executed. But the thing I kind of want to emphasize for today's conversation is that they are not necessarily things that you will have under your control. So the first thing that happens is the Snowflake will check if this query has already been run and can be returned from what's called a result cache. I don't have exact numbers on this, but I would guess that queries hit the result cache way more often than people would think. Like probably something in the range of like 10 to 20% of queries are a query someone is running again or has already run, and Snowflake just gives you that for free. Like you get this giant result cache, which is amazing. Our product runs on Snowflake, and it's has kind of a dashboarding element to it. So like when people go on it, they get all these views rendered. We use Snowflake as our backend, and I know for a fact there like 50% of our queries get served from the result cache because like someone clicks on a page, and this would be true with like a BI tool, all those queries have already run. So Snowflake just returns them straight from here.
Yeah. And I've actually used that, like you just mentioned, like a BI tool. I've done like at 8 o'clock in the morning, like I executed a query that I knew was going to cover what most people were going to do during the course of the day. You'd run that query, populate the cache, and then everybody had, sub-second performance for the rest of the day. So
yeah, and this is super helpful, right? Because what do people do when they get on a dashboard? At least this is my experience at Shopify when I used there. Even though you'd put it to run on a schedule, everyone would go and smash that run button, right?
Yep,
and
exactly.
It if you don't have this in place, it can be such a waste because you're just rerunning on data that hasn't refreshed yet. So this is not to go too far in a tangent, but this is like this little red box number 2 is like one of the most probably underrated features of Snowflake that this reminds me now I should probably do a little LinkedIn rant about this thing that is, silently powering most of the queries running, but that you kind of get out of the box. So anyways, this is important to know, to tie it back to this conversation, like this is important to know because when you, oftentimes when people go to like optimize a query or test it out and they run it twice, the second time they run it, they will hit this result cache, right? So that's something to be conscious of is like, if you, are doing testing or sometimes notice your query runs way faster, it can be because of this result cache lookup. So we could talk more about like when the result cache gets hit and, how to design your query to make sure it hits the result cache. That could probably be a bit more of a deeper talk we do, but know that that's often the first, after like authentication, which happens in the cloud services layer, this is often one of the first things that Snowflake will check is like, can we just serve this to you really quickly? Let's, for the sake of this example, pretend the answer to that is no. We next move on to query optimization. This is, these kind of next steps are things you don't have control over for good reason. Like part of what makes Snowflake easy to use is you don't have a million different dials that you need to try and turn. So Snowflake engineering team is very smart. They work very hard on making sure Snowflake can come up with the best way to execute your query and come up with the best plan to execute the SQL you wrote. And we'll talk about this in a second when we stare at a query profile. So Snowflake comes up with a plan for how they're going to run your query. They do things like transaction management, where they check if there's like other queries potentially updating the table and whether they should lock it. They do infrastructure management, like spinning up these virtual warehouses, which we'll talk about next. So all that happens magically in the cloud services layer. Then we move into the compute layer where the actual query execution happens. So we've sent this query, so it didn't hit the result cache. Snowflake has figured out how to execute it, and it said, go run on this virtual warehouse. That's where Snowflake will actually read data from remote storage. So in this case, it could be fetching data from Amazon S3 or whatever the underlying storage layer is, bringing it back to the virtual warehouse, churning through those results, and then sending them back to the client. So that's kind of like the end-to-end life cycle of a query. And just to reiterate, like the thing that you will have the most control over is how the query is written and performing this execution. Like other than the result cache, you can write your query in a way that it may or may not hit the cache. You don't really worry or think about what's going on here. but it's still helpful to have a mental model of, okay, those are like the first maybe couple hundred milliseconds of a query, and then the rest can happen in here. Are there any questions or like things that you want to add there?
No, I think you've covered. It was good coverage there, so I'm good.
That did just make me actually think of something. So, and I think we'll talk about this a bit more once we get into a pruning conversation, but I have seen some customers who have very long query compilation times. I don't know if you've ever seen this. So if you look at the query history, like if there's a column called compilation time, and then there's another column called execution time, and together with a few other components of query time, it makes up total elapsed time. Oftentimes execution time, what happens in the virtual warehouse is the biggest component of that time, and that's what we're going to spend today focusing on. But there are some cases where compilation time can be high, and that is usually when, from what I've seen, is when tables are very large and have tons of different thousands or millions of micro-partitions. It just makes it much slower for Snowflake to figure out what's the best way to analyze this data. I have to like go look through all this metadata to figure out which micro-partitions I care about. So sometimes this could be a factor that's helpful to understand, but I would say 99% of the time, you don't have to think about it.
Great.
Okay, cool. So like very quick little bit on virtual warehouses, and then we'll kind of jump into like the most important technique, which is pruning and clustering. So this is important to keep in mind because you hinted at this earlier in the conversation. It's common for people to be tempted to just jack up the warehouse size. Why does that work? Snowflake does what they call t-shirt sizing. It's an intuitive way to, rather than saying, 4 nodes, 2 nodes, it's a much easier way to reason about how big this compute cluster you get. So virtual warehouses are just an abstraction over, again, Snowflake runs on these different clouds. Each of these clouds has like compute instances they provide as like a raw primitive. A virtual warehouse is just an abstraction over that. They've sized them according from these feature sizes extra small to I think 6XL is the biggest one. I've never personally touched one of those, but if you have a real hairy job, you could do that. So the two key things to recognize when you use these, and I think we would have touched on this in our last session, but just a good recap is each time you increase the warehouse size, you double the number of nodes or compute instances in that virtual warehouse or in that cluster. So that's one. So you get double the amount of memory. Each warehouse has a bit of disk space on it, so you double that as well, and you double the number of cores, which allow you to kind of do more in parallel. So naturally, by doing all that, by throwing more memory, more disk space, more compute processing cores at the problem, it will often run faster.
Right.
Or almost always, up to a certain extent, which we'll get to. But the key thing is like you are now, requiring twice as many computers, and computers cost money. So your cost doubles as you would expect because you're exactly doubling the number of resources each time you increase your warehouse size.
Right. The one thing just to add quickly here, and you kind of touched on it, those of us who have come from, like you said, the Teradata world and some other things is this is now where if you have different organizations within your company that are doing different things, you can avoid contention, right? All trying to share one pool of compute is you could set up, here's your warehouse and your queries and your queries aren't contending with one another.
Yeah, exactly. And another kind of helpful thing that's useful to set it up is like, you may have some really small queries and you want to run those, or you will. Most people have lots of small queries that will fit on an extra small just fine, but you will inevitably have some bigger beasts you have to deal with, let's say, and maybe you want to create like a medium or an extra large that you throw those really hairy jobs at that you want to like quickly go and reprocess a bunch of historical data. So there's a ton of flexibility here. I think we can do, and we should do another session on
Part N,
virtual warehouse best practices. Yep. But I think for the purposes of query optimization, which is today's focus, just kind of touch at a high level, like to your earlier point, you may be tempted to increase the warehouse size. How often will that work? And what are the trade-offs there? So to think about that, and I'll just touch on this very quickly, we have a blog post on this kind of at the bottom of the slide, with a hopefully fairly easy to memorize URL, but we can share a link as well that dives into this in more detail. But at a high level, like increasing the warehouse size is a way to make your query run faster, sometimes at the same cost or sometimes at cheaper cost. But the key thing to emphasize is this will only work up to a certain point. And the way to kind of understand that with this diagram is we have, on the y-axis, we have like execution time and cost plotted with these two lines. And on the x-axis, we have where the warehouse size. So as you say we take, and this is like hypothetically with the same query, like what you get if you were to run this query on each warehouse size is these two hypothetical curves where you start with an extra small, and let's say you run this query on a small. What happens when we do that? As a recap, you're doubling all of the resources you get. So if this query has lots of data to process, and I want to emphasize this, all that data and work can be evenly spread across all those resources, then you will get a doubling in performance because you've thrown twice the amount of resources at it. And even though the cost is doubling because Snowflake bills you for the amount of time your query executes, your cost actually stays flat because each second costs twice as much, but you're running for half the second. So those two cancel each other out. Does that make sense?
It does. Yep.
Cool.
Absolutely.
So basically what happens is you can keep doing this and up to a certain, you'll keep seeing your cost cut in half, your query execution time cut in half, and your costs stay flat. That happens up to a certain point. What happens at that point? Eventually it doesn't, you can keep throwing more and more compute at this thing. You don't have enough work to be spread across all those computers, I think is the simplest mental model to use. So It no longer, Snowflake will make the correct decision. Hey, we actually can't do any more with this, or it would actually cost more to try and break up this work even further. So we're not going to do that. And that's where it starts to cost more to process the queries when you run it on a larger warehouse size, because the execution time isn't changing. It's now gone flat, and now we're just paying double the amount for each thing. So this is an important thing to talk about, just because it can often be a quick win if you, particularly if your query is running out of memory, right? So when you run to memory, I don't know if we'll get into this today, but your Snowflake intelligently spills to disk to start with, and then will eventually spill to remote storage if it can't spill to disk anymore. That's very slow and can be expensive. So oftentimes increasing the warehouse size can be a quick win because that disappears and your query can even more than double in performance because it's no longer having that memory issue. So this is an important thing to keep in mind is, but I guess I would caution, before doing this, are you check, are you actually memory constrained? And are there other kind of anti-patterns we could fix with the query before we go to actually increase the warehouse size?
Yep.
Yeah. And anything you would add there?
No, I think it's I've been in that position where, especially the first few times with queries is it's finding that balance, right? It's analyzing your query and what you're going to be going through now, and don't just, hey, I've had this, large sitting around, I'm just going to throw it at it, right? I've seen it really takes a lot of trial and error to kind of find that sweet spot, right? Where you have that right balance of the right size of virtual warehouse and as much optimization you can do in the query. So
cool. All right, let's keep motoring along. I think we're at 18 minutes here. So I want to jump into the query profile, which, the query profile, if we reflect back to, kind of this slide, remember, this is where you can focus your time optimizing. Snowflake provides a really great tool to understand how is your time being spent on this query execution stage. And that's where you use the query profile. So you can access this in a couple places. One is I don't have this shown in the slides, but you can, it's fairly easy to find from the query history. If you click into a query in Snowsight, you can get this nice rendering of the query profile. You can also actually access it programmatically as well. There's a new function called get query operator stats. For most users, they will not need to use that. It's have you looked at that? It's a tabular output of all the.
No, I haven't.
It's not something you would stare at when you were trying to debug a particular query. Where it's useful is if you want to programmatically analyze lots of queries to identify some of the patterns that we're talking about.
Yep, that makes sense.
Cool. So kind of a couple things I understand with the query profile. One is, especially for people who are new to SQL, the SQL you write, if you kind of read it from top down, isn't necessarily the order that it gets executed in, right? This is where we talked about the cloud services layer. It comes up with a optimal plan of like, what is the fastest way to execute this logic someone has written? And Snowflake, boils your SQL down into different stages that it actually executes. So if we look at this simple query that's using kind of one of the data sets you get out of the box. So actually anyone today could go and run this account and run this in their account and reproduce it. You have a table, a from statement. So you're selecting some columns from this table, you're filtering, you're aggregating, and you're sorting. Snowflake boils those down into these different stages. So, a from table will always result in a table scan. Your where filter will turn into filtered clauses. Your group bys and aggregations turn into an aggregate, and then your order by turns into a sort. So this is one of the first things I recommend people do when they look at a query profile is like familiarize themselves with what was the query written and what are all the stages in the way that Snowflake has compiled this query, and then how do those two relate to each other? Starting to build that model of like, oh, this table scan, that's this from statement that I wrote over here. And oh, this aggregate, that's doing all these group bys that I talked to. And why that's helpful is when you go to like start to look at the statistics and understand which of these are taking the longest amount of time, you can map that back to the mental model of like what that query is doing. Does that make sense?
No, it does. And I like the way you graphically showed that the side by side, understanding the query structure and then, what's being presented to you. That's a great way of looking at it.
Yeah. And like, I can't show this with this static image, but part of the way, this is a simple example. So it's like, there's only one table scan here, right? So you can very quickly be like, oh, that table right here, do the mapping. But as you get to these bigger kind of hairier queries, what you can do to understand this is you can actually in the UI, you can click on each of these individual stages. And that will reveal, I think I may even have okay, perfect. So here I've kind of showed that when you click on, or maybe I'm calling them a node here. When you click on a node, it actually gives you this information. So you can see, oh, here's the table name and here's the two columns I've selected. So if you had a query, which is not uncommon, that read 10 tables and you're trying to figure out, oh, which one is this mapping to? You click on these.
It'll tell you for you. Yeah.
It'll tell you like, oh, okay, this is this group by here. And you can kind of then do that mental mapping between the query profile and the query, the SQL text itself. Okay, so what do we get here? Kind of one of the most important things to look at is the execution time summary. Okay, so what this is telling you is it's giving you a breakdown. This query took 4.5 seconds to run total, and we spent 32% of that time processing, 0.3% on local disk I/O, 67% on remote disk I/O. So oftentimes, like what I typically look for here is like, am I spending more time reading data or processing data? If you think back to our kind of life cycle of a Snowflake query, you have this remote storage and you have the compute layer. So remote disk I/O would be referring to these arrows here, spending the time spent kind of fetching data from that remote storage. If data is cached locally on the disk space on each warehouse, that would appear as local disk I/O, as like the operations reading to and from. And what that kind of tells you is where to start to begin to potentially focus your efforts, right? If most of your time is spent reading data from remote disk, then your solution is how can we minimize the amount of data that has to be read or scanned from remote storage, which we'll talk about maybe in a second, or maybe in a part 2 where we do a deep dive into clustering. Probably I'll still be part 3. So, that's kind of one of the things I look at. Or if it's processing, like you can just as maybe not just as often, but often see like processing time be the big factor, and that can typically be, okay, how am I actually processing that data once it's been read? After I've done this from statement, what am I doing with that downstream? Is that the bottleneck? And where you can see this explode be a very, I gave away what I was going to say, where you can see this, often be the higher portion is like, let's say you've done something like you have an exploding join, right? So you're, vastly increasing the number of records that your downstream operations have to process, which makes you spend most of the time on processing. So that's a helpful kind of thing to look at, is like build that mental model of like, where's my query spending all this time? And then that will lead you to figure out how to actually go and figure out how to optimize this. Partition scanned. So I was going to show this later, but in the storage layer itself, each of the tables are split into what are called micro-partitions. The mental model for micro-partitions is they're just files. So like, that's what a file is in Snowflake terminology. It's a kind of a chunk of your data. It's a micro-partition. That's what they call it. And what's helpful here is what Snowflake is showing you is how many micro-partitions are available across all the tables in your query. So in this case, there's just one table being read. So there's 3,200 micro-partitions in this table. And partition scanned is how many of those micro-partitions in remote storage did we actually have to read in order to get the data that's relevant for the query execution. So if we think about this, we've filtered on year of the order date is 1997. So there are more years than just 1997 in the table. We don't have to read all of those. And it's telling me that we actually only had to go and look through 491 partitions to get the records relevant to that. Does that make sense?
No, it does. And I think, that's a good point there is oftentimes when you're joining to these tables that are very large, what can you do from a predicate perspective to limit the amount of rows you're going to need to process at some of those? Like you said, if I only need 1997 data or I only need something from a certain region, add that additional filter, right, into that so that you're not processing all that data that in reality you don't even need to look at.
Exactly. And I think this is a nice kind of way to lead into the next topic we'll talk about in part 3, which is clustering and query pruning. Oftentimes, and here's kind of how I'll tease this, oftentimes when you write a query like this, when you filter on a date and set that value, Snowflake can go out and figure, okay, there's all these years of data. Here are the relevant micro-partitions that contain the year 1997. I'm only going to go read those. Where that can go wrong is like, let's say your data was randomly kind of sorted and inserted into this table, right? So remember, micro-partitions are files. So you could, like, as a simple example, let's say you had 6 micro-partitions and you had 6 years of data in this orders table. If the data was perfectly ordered, your first partition would have 1 year, call it 1996. Your second partition would have the next year, 1997, third partition, 1998, so on and so forth. So Snowflake would know, like, when you filter on 1997, I only need to look at that second micro-partition. That's what has everything. The only way that it can do that is if that data has been kind of organized in that way in those micro-partitions. So if it hasn't, if they were kind of randomly, like each partition contained a mix of 1996, 1997, 88, 99, et cetera, then Snowflake, what you would see in the query profile is 3242 micro-partitions scanned and 3242 micro-partitions total. That means it actually had to read through all of those before it could go and do that filtering to get down to 1997. And that's what can often make your query take a bunch of time. The other case where you'll see that is like if there's no filter in here, then it will have to read all of them, obviously. So that's one of the biggest culprits. So if, typically when I look at queries, I see remote disk IO is taking up most of the time. And you can kind of see that reflected here as well. These blue bars show like the proportion of time spent on that particular stage. This remote disk IO in this table scan stage is where most of the time is spent. And then the question becomes, can we either, like you said, can they throw in a filter there? And if they have thrown in a filter there and we're still spending lots of time on this query, on this stage, then that means maybe the table isn't as well clustered as it should be. And we'll save that for a future session.
Yeah. Wow. This was very, very lots of great information, and I'll bring back our basis here for everybody. that was a wealth of information, and as you've all heard, we're gonna have to go into a part 3 and part 4. Who knows?
Yeah.
But that's great, and I think this is really important because I think people understanding what they're running and what they're doing and how to read that is great. So again, if anybody has any comments, please put some comments on below in the video to give us some feedback in terms of what other information you might want. But it does look like, Ian, we will be scheduling a part 3 to continue from what we are doing.
I promise to go faster. I feel like each time we have all these ambitions, and then but I mean, hopefully, let me know. Like, yeah, I'd love to hear in the comments. Like, is this too in depth? Do we want to go faster over this stuff and spend more time on the other stuff? I'm happy to do that. It's always tough to understand like where people's knowledge is and like where they want to focus. So that feedback's super helpful. But like otherwise, we'll just keep planning to going through.
We'll keep on going.
Yeah, our next session we'll plan to do kind of clustering and pruning unless we hear otherwise.
No, that's perfect. And we will share the link of any of the information, the blogs that you talked about, some of the earlier slides. But other than that, Ian, thanks again for joining us for this episode. And we'll look forward to the next one.
Yeah, likewise. Thanks for having me.
Great. Thanks, everybody.
Bye.